Okay, so we'll start with centrifugal casting today. We'll quickly summarize what we had seen in the last class. We saw investment casting, right? That was one major manufacturing process that we saw, right? Investment casting. We're discussing the special casting processes, starting with your sand molding, what we saw at the very beginning of the unit. Then we saw investment casting, shell molding.
Sorry for disturbing. Please take the attendance after 5 minutes, sir.
Yes, sir, sure.
Okay.
So, yes, shell molding and then investment casting, right? So, as we had seen investment casting, you have a wax pattern. You see here that will give you the idea of the process, right? What we've seen in the last class. With the help of this wax pattern, right, that you produce out of an injection mold, we will make an assembly of those patterns. We'll dip it in a slurry, right? And once you have that coating, right, multiple coatings, then we will heat that assembly so that the wax comes out and you have the shell. Then we'll pour the molten metal and shake it out so that you have the final casting, right? That shell, what had been formed here, will be shaken out either mechanically or manually, and you get the casting, right? So the pattern to the casting to be made exactly resembles the pattern. So that was the investment casting process, right? We discussed this in the last class. I put those video links as well. Okay, applications. And now centrifugal casting. Any doubts from the last class? Okay, so you see centrifugal casting, right? As the name suggests, you have a centrifugal action that is what is the principle of this casting, the centrifugal force, right? The force that tries to act away from the center, right? So centrifugal casting or roto casting is also another name for it. Is a casting technique that is typically used to cast thin-walled cylinders, right? As you might have guessed, when the material flows away from that axis, it tries to go outwards, and you have, especially for thin-walled cylinders, we are using this, right? It is noted for the high quality of the results attainable, particularly for precise control of their metallurgy and precision, because the way they are going away, right, will form the crystal structure, and that will lead us to having some properties which are desirable, right? You are studying materials this semester. To understand this, what I'm talking about, the microstructure represents, the microstructure decides the behavior of the material, right? The type of microstructure. If you can manipulate the microstructure, you can manipulate the properties, mechanical properties that is required as per the application. So that control we have here, right? Because of the crystal structure that we are able to form, right? Because of the centrifugal force. Unlike most of the casting techniques, centrifugal casting is chiefly used to manufacture stock materials in standard sizes for further machining. So primary shapes is what you can say, like blocks of material, billets of material, right? Or what do you call them? Rods, etc. Okay, so all those will be, they have to be further machined, right? But the primary shaping that is done is through the centrifugal casting, right? rather than shaped parts tailored to a particular end use, right? As we have, for example, in investment casting, right? But here we are trying to make standard sizes, right? That is, centrifugal casting is known for that. Right? You will see a video, right, to understand what we are talking about. Please confirm if you're able to see the video and hear the audio. Yes. Yes, students. Is the audio and video okay? Then 18 H51 171. H51 171. Okay. Okay, so you're able to see it, right? And hear the audio. You see, with the help of mechanical attachment here, these barrels are able to rotate. Okay, they are made to rotate, and when the molten metal is poured in, it gets and distributes throughout the circumference because of the centrifugal force, right? Because they are rotating at high speeds. So that is what helps the material to accumulate on the periphery, right? Very simple. Just as you have in the washing machine, right? The clothes get try to get away from the center. Same thing here. Okay, this is kind of the orientation is not as you have in the washing machine, right? It's 90 degrees to that. So you observe that this is the molten metal being poured, right? And with the help of these channels, it will go inside this setup. So you see, now you understand what this text means. In centrifugal casting, a permanent mold, right, as you have seen, is rotated continuously about its axis at high speeds. This is the range of speeds that we are talking about, 300 to 3000. Depends on the density you are trying to achieve. The speed would increase, right? In the material, as the molten metal is poured, the molten metal is centrifugally thrown towards the inside mold wall, where it solidifies after cool, right? It is usually the casting is usually a fine grained casting, right? It's not coarse grain, it is fine grained, and you might have studied or you will be studying in materials that a fine grained casting, a fine grained structure would have a higher hardness, okay, more strength. So, and basically ductile materials would have fine grained, I'm sorry, brittle materials would have fine grained structures. So that is what we are trying to achieve here. Fine grained casting with a very fine grained outer diameter going to chilling against the mold surface, right? As you have seen, because the outer part of that die, what we have seen, will cool down first, right? Because of the atmospheric air. So that gives it a very fine grained structure on the outer diameter, okay, of the casting as compared to the inner one. Impurities and inclusions are thrown to the surface as obvious of the inside diameter, which can be machined away, right? Inclusions would be forming on the outer periphery, so you can machine that, right? So those impurities and inclusions can be removed. Unlike your normal casting, sand casting or shell mold casting, you don't have this feature, right? That you can have it on the surface and that can be removed later. But here, because of the centrifugal force, they are thrown to the surface. And that's why you can machine them. Casting machines may be either horizontal or vertical axis, right? We have seen a horizontal one in that video, but it could be a vertical one. Right? The axis orientation could be vertical. So horizontal axis machines are preferred for long, thin cylinders, vertical machines for rings, right? Most castings solidified from the outside first, as I have told you, because the atmospheric air in contact with that mold. This will be used to encourage directional solidification, right? We have discussed what is directional solidification. That you are trying to manipulate the, what do you call, the direction of solidification, right? It should start solidifying from this point and proceeds all the way either inside or outside like that. So directionally solidified, trying to manipulate the solidification direction. So that is what is achieved and thus gives useful metallurgical properties to it. Often the inner and outer layers are discarded and only the intermediate columnar zone is used, right? Machining basically to only use this intermediate which is in between, right? The columnar zone. Centrifugal casting was the invention of Alfred Krupp, right? That's what the inventor name is, who used to manufacture cast steel tires for railway wheels back in 1852. Okay. Doubts so far? Okay. You see features of centrifugal casting. The castings can be made in almost any length, thickness, and diameter. Different wall thickness can be produced, right, from the same size mold. Depends on the speed, isn't it? More the speed you provide, less will be the thickness. It will get more dense, right? So that wall thickness can be manipulated. Eliminates the need for pores, isn't it? Because we are able to produce hollow structures, but without the help of a pore, right? Unlike your sand casting or any other type of casting. Resistant to atmospheric corrosion, a typical situation with pipes, right? So pipes is what usually we know gets corroded, right from the top surface. So you're able to produce hollow pipes and they are resistant to atmospheric corrosion. That's a win-win situation. Mechanical properties of centrifugal castings are excellent, right? Because of the dense microstructure and the fact that you are able to remove the inclusions, right? You are able to move them, throw them out on the outer periphery, and then you can machine that away. So that gives you the properties required, mechanical properties. Only cylindrical shapes can reproduce this process, right? That's the disadvantage, you can say. Size limits are up to 3 meters or 10 feet in diameter and 15 meters or 15 feet in length. All thicknesses range from all these. So this has been produced, right? If you're talking about mm, 2.5 to 125 or 1 to 5, 0.1 to 5 if it is in inches. Tolerance limit on the OD that can be achieved is 2.5 mm, right? And on the ID can be 3.8, right? So these are the features of this type of casting process, the centrifugal casting. Benefits, as I said, thin walled cylinders are difficult to cast by other means. Centrifugal casting is particularly suited for them, right? So thin walled cylinders can be made. Centrifugal casting is also applied to the casting of disc and cylindrical shaped objects such as railway carriage wheels, machine fittings, right? Railway carriage wheels, if you have seen, disc-like structures. So that can be made because they require certain properties, right? As I said, more dense, and those crystal structures should also be in a particular direction so as to be able to take up the load, etc. So you see there where the grain flow and balance are important, the durability and utility of the finished product, right? That is what will decide the durability and the utility of the finished product that is required in the at the particular application. Provided that the shape is relatively constant in radius, non-circular shapes may also be cast, right? So not just completely constant, absolutely constant, you can say, even if it is a relatively constant radius, right? Then even those non-circular shapes may also be cast. Materials that can be cast with centrifugal casting. You see, all these iron can be cast, steel, stainless steel, especially glass, even, and alloys of aluminum, copper, and nickel. These are all the materials that you can cast. Parts, as we have seen in that example, pipes, right? Boilers, pressure vessels, isn't it? Those are also thin-walled cylindrical entities. Flywheels, right? Because they are required to have dense structures to be able to store the energy, isn't it? Cylinder liners, even other parts that are accessible, right? That is symmetric about an axis. That's what it means, right? So that this centrifugal casting is known for producing parts that are accessible. See here, this is another diagram, right? Even for exam point of view, and to be able to understand the concept, right? Through a diagram, you can refer to this, right? You have this ladle containing the molten metal that will be used for supplying this molten metal to this cavity, this setup, right? You have rollers here, right? You see bottom rollers, then top rollers, right? Two sides. One would be driving in. You see here in this case, bottom rollers are the driving members. A motor will drive this shaft, and the shaft is connected to the rollers. So the rollers will move, and because these bottom rollers are attached to this setup, right, or what we call a mold technically, the mold will rotate, right? And while it is rotating, we'll supply the molten metal, right? That's what we saw in the video. So that happens, and this top rollers will also, because they are attached, they will also roll. Basically, trying to have some restriction there, right? So that this doesn't move. This mold stays in place because of the two rollers. Because of the bottom rollers, it rotates, right? So once you have poured the molten metal, because it is what do you call it? Rotating continuously, because of the centrifugal force, the molten metal will go and sit at the periphery, and therefore you get this finished casting in the end when it is solidified. You see, this is a 2D diagram of the same thing, right? This can be drawn as for the exam point of view. So that's what gives you the gist of the process, right? We have seen the video, right? You see here, thin, isn't it? Quite thin. So these kind of components are being made. These are typical products fabricated or manufactured by centrifugal casting, right? Doubts? No doubts? Okay. So you see the next type of casting is die casting. Okay, that's the top heading, die casting, and under die casting you have cold chamber and hot chamber die casting. So essentially what you're seeing is die casting. So cold chamber die casting is the second of the two major branches of the die casting manufacturing processes, right? You see the videos attached, but let us have a look at the process first. Okay, 2D diagram. So you see here, this is your mold, right? And that's your cavity here. Okay, this will be supplied by molten metal. So basically, what we will do is we'll supply this plunger, right? Would be on the extreme right initially. We'll supply molten metal through this opening here, right? Once the molten metal has been poured, this plunger would move to the left, right? As it is now, it will push this molten metal into this casting cavity, right? This was initially empty, and once the molten metal is poured and this plunger moves, it applies that pressure, and therefore because of that pressure, it enters this cavity, right? So this mold has to be made, right, initially of the required dimensions of the casting, so that once it solidifies, it takes the shape of that cavity inside, right? Very simple. You see here, pressures of 3000 pounds per square inch psi. We're talking about megapascals, right? Which we usually do 20 to 350. Okay. So those pressures may be used in manufacturing industry to fill the mold cavities with molten metal, molten material during cold chamber die casting manufacturing. Okay. So to be able to push that molten metal inside, this is the general pressure range. Castings manufactured by cold chamber die casting have all the advantages, characteristics of the die casting process, such as intricate details can be made in walls, superior mechanical properties can be achieved. Okay. So integrate details because we are trying to push that mortar metal, right? Take the shape of that cavity inside. So integrate details can be made, right? Unlike your sand casting, etc. Then you have omitted some details and then you'll try to machine it later. But here, in just one go, we're able to create the integrated details. Thin walls even, right? Because of the thin cavities that you can make. And I mean in the mold cavity, okay, in the mold. Superior mechanical properties, right? Because of the pressure that you're applying, you will achieve the properties that you require. Significant initial investment into this manufacturing process makes it suitable for high production applications, right? The investment is high initially because to be able to design that mold, right, requires a lot of research and development, right? To be able to come up with all the dimensions, right, considering all the parameters, right, thermal and mechanical structural parameters, all that, considering all that. So that requires a lot of investment, initial investment. So, but it will pay off when you're trying to use it for mass production, right? Like one mold is able to produce maybe 100 or thousands, even 10,000 sometimes. One mold is able to produce even 1,000 to 10,000 components. So that if that is a high production application, then that initial investment, which is high, will be justified. Okay, that's what it means. You see, we'll now look at the video. You see, that's the mold cavity that I was talking about. Okay, to be able to make this mold, okay, fabricate this mold requires a lot of research and development and therefore cost, right? So that is where this mold metal will flow and sit. Okay, once you have applied that pressure on the plunger, that mold metal will be forced to take the shape, right? This hollow shape. It will go and sit there. Right? Those are called ejector pins, okay, which are pushing that casting. Those are called ejector pins. That was your screw, right? Part of the heating system that is being removed. You see the level of detail that is there. This is what we're talking about. We can achieve intricate details. You can observe all those ribs and slots and all the recesses, right? Those can be achieved in die casting, right? Was that clear? Or should I replay if there is any doubt? Now you see advantages. Excellent dimensional accuracy, right? As I said, because of the pressure that we are applying, right? We are able to manipulate the dimensions and it will take the shape of that cavity, right? Mold cavity that inside the permanent mold. Depending on casting material, right? The accuracy, it is dependent on casting material, but typically we have 0.1 mm for the first to 0.5 centimeter and 0.02 for additional centimeter, right? And smooth cast surfaces, right? Because of the pressure that is applied, it will go and stick to that mold cavity. So that's what gives it smooth cast surface. A reference value of 1 to 2.5 micrometers or 0.04 to 0.1 tau, that is US units. Thinner walls can be cast as compared to sand and permanent mold casting, right? Approximately of this range. Inserts can be cast in, right? Such as threaded inserts, heating elements, and high strength bearing surfaces. And reduces or eliminates secondary machining operations, right? As I told you, we are trying to make it in one shot. So the secondary machining operations are avoided because we have excellent dimensional accuracy. That's why. Rapid production rates, right? This is very much suited to mass production, we can say, right? And we can even automate this. That is not written here, but it is even automated. Very much likely a candidate for automation, right? That is basically reducing the human assistance in manufacturing. Casting tensile strength as high as 415 megapascal, right? And casting of basically tensile, tensile strength, right? The ability of material to undergo tension, right? The strength that it can withstand, the stress that it can withstand before yielding. So that gives it tensile strength, or if it is ultimate tensile strength, then we're talking about the highest stress that the material can take, right? Casting of low fluidity metals, right? Those metals which are not able to, the fluidity is basically the ability of material to flow, right? So if a material is having a property that it doesn't offer much fluidity, right? Flowability, then for such cases we can go for this type of casting because that plunger is able to make up for that loss of fluidity, right? Or a low fluidity problem that we have. Disadvantages, very high capital cost, right? As I said, making of that mold requires a lot of time and effort. Therefore, to make die casting an economic process, a large production volume is needed, right? If you are going for mass production, it will pay off. Other disadvantages include process limited to high fluidity metals, and the casting weights must be between 30 grams to 10 kg. In standard die casting process, the final casting will have a small amount of porosity, okay? Some kind of, what do you call, not so solid component, okay? A small amount of porosity. This prevents any heat treating or welding because the heat causes the gas in the pores to expand, right? Which causes micro cracks inside the part and exfoliation of the surface, right? So that heat, right, when given, because there is gas in the pores, right? Porosity, that's